Ladies and gentlemen, in this session I'll give you an introduction to probability. Even though probability is not included, specifically included in your syllabus, syllabus actually starts with the random variables, but I strongly recommend that we revisit some basic concepts of probability. So let me start with that presentation. So this speech is organized into your learning outcomes, then the basics of probability, then you will see the three definitions of probability, the classical definition, the relative frequency definition, and the axiomatic definition. Then you will see things like definitions like what's an event, what is a sample space, what is experiment, etc. Then the summary of understanding. What you will learn, you will review the theory of probability. Then you will simulate a coin toss experiment with Python. I will show you that code, and we will toss some coins and see, verify the concept of probability. Actually, we will verify something called the law of large numbers. Then we will revisit the three definitions of probability: the classical definition, the relative frequency definition, and the axiomatic definition by Kolmogorov. Then you will learn the meaning of sample space, event, Borel field, and experiment. These concepts should be very clear. Now, the concept of probability was originated by an Italian mathematician, Girolamo Cardano. This Girolamo Cardano was an inveterate gambler. During this game, he understood many patterns in the game. He summarized his observations into the book called Book on the Games of Chance. That was the first book on probability. Actually, Cardano made some other groundbreaking discoveries also. It was Girolamo Cardano who proposed the concept of a complex number. Although he didn't completely believe that, he apologized for that, but he put forward that idea. Then he devised methods for solving cubic equations, etc. And then French mathematicians, the French nobility had a lot of time and money for gambling, etc. So many French mathematicians furthered this theory, like the Bernoulli family in Paris, the people like Johann Bernoulli, Jacob Bernoulli, Daniel Bernoulli. They were all great mathematicians. They all contributed to probability and random process. Then Borel, then Kolmogorov, who proposed axiomatic definition. Then many others like Wiener, etc. They all contributed further. These are some of the names. And we will revisit the definition of probability. Most of you are familiar with the classical definition. So what is the a priori probability of an event? That is, if NA is the number of favorable outcomes and N is the total number of outcomes, the a priori probability of an event A, that is given as a ratio NA by N. And what is this a priori probability? A priori probability means that probability measured without actually performing the trial. Say, for example, in a horse race, I can speculate or I can compute the probability of a certain horse winning even before the horse race, or even if the horse race hasn't been conducted, I can still talk about the probability of a horse winning. So that is the meaning of a priori. Without performing the actual trial, you can talk about the probability of an event. That is NA by N. If NA is a number of favorable outcomes and for A, and N is the total number of outcomes, then that NA by N, that is the a priori probability of an event. Now, so this comes as a ratio. Now, we have to toss a coin and see. Say, suppose I toss a coin, what's the probability of getting a head? That is, you say that, what do you say? There's only one head, so you can say that the number of favorable outcomes is 1, and there are two cases. It can be, I assume that the coin does not fall on its edge. So I can say it either falls as a head or tail. So I have two possibilities, either a head or a tail. So of which the probability of getting a head, that is 1 by 2. Now actually we have to toss some coins, and you can see that. We will see how that behaves. So for that I have written a Python code. I will show you how that is executed. Now this is not the best way of programming. So here, since you are not right now, some of you may not be familiar with Python programming. So here I do what I do is I import the module numpy. That's a numerical Python that I import numpy as np. This is a specific name I given here because every I can write as np. Anywhere I can write as np, and I can save some typing. So I say I toss a coin say 100 times. I keep a threshold say 0.5. So I assume that my coin is a fair coin. So the probability of getting a head, that is equal to the probability of getting a tail. So then what I do is I some array I initialize to a blank array, out ARR, that is a blank array. What I do is then I create a random number, np.random.rand. Actually, this creates a random number, a uniformly distributed random number in the interval 0, 1. So this x is a random number between 0 and 1. So if this x is greater than threshold, then I say it's a 1. I take it as a head. I take head as a 1 and say tail as a 0. Okay. So if this x value, if this random number is greater than this threshold, that is 0.5, to this out array, I push a 1 into this out array. If this is less than the threshold, if this x is less than 0.5, then I append a 0 to this out array. Okay, so this is how I do that. This is a syntax for a for loop. For I in range is the numbers 0, 1, 2, 3 up to n. So these range n means this is range 100. It's these are number integers from 0 to 99, excluding 100. So there are 100 values in that. So for these things, I compute this x, then every time I put a new random value, it's just like tossing a coin. So if x is greater than 0.5, I say this is a 1, out array is a 1, 1 is appended to this, or else a 0 is appended to this. So then I print this out array. You can observe this thing. Then you will see a random pattern of 1s and 0s. Then these head, I assume that's a 1. So I count the total number of heads because these contain only 1s and 0s. 1 is a head. So if I take the sum of this array, that will be the number of heads in that. So I take the sum, np.sum. This np is actually numpy. Okay, I imported numpy as np. So here it is np.sum out array. Okay, what is the sum out array? That is the np.sum out array is the total number of ones in that array. What is that? The total number of heads in that. So I toss this coin say 100 times, how many heads have come. So typically you expect that there should be around 50 heads should have come. So that thing is divided by n, so that this p is the probability. So 100 times I toss a coin, what is the probability of getting a head? So what happens is I say that the probability of a head is plus this actually a string, print this string, plus REPRP means whatever value of p that is coming, it will appear here. So we will execute this code. So this is here, I take a terminal, and I strongly recommend that you have a Linux system with everything Python and everything installed. So I am using Python 3. So I use an interactive Python environment, IPython 3, in which I run this code, I run this coin toss, Now you can see that I toss this coin 100 times. So this is the array. First, when I tossed, I got a tail, then I got a head, then a tail, a head, etc. Okay. So what is the probability of getting a head? It is 0.54 now. Okay, it is 0.54 now. Now you do this again. You can see you will get a slightly different value. You can see that the probability of head is 0.47. You toss it again 100 times. It is say 0.54. Okay. Now I can increase this number. If I make this number, say I will make it a 10,000. Okay. I make n equal to 10,000. So what will happen is you see 10,000 long vector of zeros and ones, and you can see that the probability of a head now becomes 0.5026. It is coming closer to 0.5 because I made n very large. I toss the coin 10,000 times. Now I make it very large. So as I make n very large, then what will happen is this probability will tend more and more to 0.5. So that is the concept of a law of large numbers. So now I have some 10 raised to 6, 1 million times. I'm tossing the coin 1 million times. So here I turn the coin, it takes some time, there are 1 million toss. Now you can see that it has, the probability of the head has gone much nearer to 0.5, 0.500243. I will try to put one more zero. I don't know what will happen. Whether my system will stand that, I'm not sure. Now I'm running this for 10 million times. It works. Now you can see that it is much nearer to 0.5. It is 0.4998772. It is becoming very close to 0.5. So this is the concept of a law of large numbers. The more number of times so suppose I toss a coin 10 times, I may get 3 heads or 7 tails. Sometimes I may get 7 heads or 3 tails. Sometimes I may get 4 heads and 6 tails. So if I make it well, say 1,000 times, so I may be getting a head between say 400 to say 600. So as soon as I make it very large, when I make n very large, then this probability of getting a head that becomes very close to 0.5. Here I have tossed it 10 million times. I have tossed a coin 10 million times. A 1 is a head and a 0 is a tail, say, I assume that way. So that now the probability of getting a head is 0.4998772. Okay, it is getting very close to 0.5. Now we are talking about a fair coin. Now what if it is an unfair coin? I'll make it much smaller, say 1,000. Okay, I'll make it say 0.2. Okay, this threshold is a 0.2. Actually, instead of this big code, I can create these random bits. Actually, I'm creating random bits. I can, with one line of Python code, you will learn these things later. But for the time being, I go in this manner. Now you can see that now when it is 0.2, you can see that the probability of getting a head is 0.794, that is 0.8. Okay, so 80% of these are ones. 80% of these outcomes are now ones. Now I make it a 1 million or something. Okay, yeah, that's a not 1 million. It is 10 raised to 5. Now we can see that it is approaching 0.8. Now it is a biased coin. It has a greater probability of a head than tail. Probability of a head is now 0.8 and probability of a tail is 0.2. So this is how I toss a coin. This coin tossing is also called Bernoulli trial. This coin tossing is also called Bernoulli trial. Okay. So tossing the coin is very important experiment in random process. So now you have appreciated the coin toss experiment and you understood the law of large numbers. Now let me go back to my presentation. Now this is how I define the probability. So that is the number of favorable outcomes divided by the total number of outcomes. Okay, but I have a problem. If you say about a coin toss, I have two cases. There is either a head or a tail. So what is the probability of getting a head? That is the favorable cases is a 1 because there is only one head and total number of cases 2. You can say, you can divide 1 by 2 and you can say that. Or if I toss a 6-faced fair die and probability of getting a 6 in that, there is only 1 6 out of the combination. That is 1, 2, 3, 4, 5, 6. So what is the total number of cases? That is a 6, so that probability should be 1 by 6. But is it always the same? If you say, if I ask you, say, what is the probability of a sunset at noon? Actually, if you argue that way, because there are only two cases, because either there is a sunset at noon, or there will not be a sunset at noon. So I have two cases. So with that, can I say that the probability of a sunset at noon, because we have never seen a sunset at noon, because sunset is in the evening. So can I say that the probability of a sunset is 1 by 2? I cannot say that. I cannot say that because because it is not logical. I have never seen a sunset at noon. Okay, I have never seen a sunset at noon. So something is wrong with this definition. Some loophole is there. Now that loophole should be closed because we need some change in this definition. So that means for this definition to hold, the outcome should be equally likely. Okay, the outcome should be equally likely. There's a equal chance of getting a head, equal chance of getting a head as well as getting a tail. So you can say the probability, but it is not the same for sunset at noon because we have never seen that. Okay, so you cannot say that the probability of a sunset at noon is 0.5. You cannot say that. Okay, but you can say that the probability of getting a head in a coin toss is 0.5. Now the definition is modified. I added one more word to that. That what is the a priori probability PA, that is NA by N, provided that these all outcomes are equally likely. Now you think that my problem is solved. Actually, my problems are starting because there are a lot of critics to classical definition. There are many problems with the classical definition. One thing is, we all know that probability is a real number between 0 and 1. Not all these numbers can be expressed as a rational number. As per the definition, this is NA by N, which is a rational number, which is a ratio of integers and natural, so it's a rational number. But you know that there are probability is any number between 0 and 1, and many such numbers cannot be expressed as a rational number. Then we say that there are many critics, but classically the probability is defined a priori, but you know that it is influenced by previous experience. If I ask you what is the probability of a sunset at noon, you all will say that is 0 because you have never seen a sunset at noon. Okay, you have never seen a sunset at noon. So even though we say it is a priori probability, it is completely devoid of experience. We know that it is not true because many of these things are influenced by previous experiences. Now there is another term problem with the term equally likely. I added this term to counteract some defects, but the term equally likely, if you say, it means equally probable, which again means that things of equal probability. Okay, the meaning is equal probability, but we cannot use such a term in the definition of probability because we started out defining probability, and in this we are using the term probability again, which is unfair, which cannot be justified. There are many other critics like the Beltran paradox, etc. I don't go into that, but I point out some critique to the classical definition. So for probability, random variables, etc., you can read the book Probability, Random Variables and Stochastic Process by Papolis and Unikrishna Pillai. It's an excellent reference in the matter. And then there is something called the relative frequency definition. It comes as a limiting case, like by this definition, by this relative frequency definition, the a priori probability of an event, PA, that is equal to limit n tending to infinity, NA by N. Rather than saying simply NA by N, it is given as a limiting case with when N is very large, this is a ratio between NA by N. But this definition also has the same defects as the classical definition. So mathematicians were at a loss. Then the giant of the Russian mathematics, Kolmogorov, he proposed the axiomatic definition. So he put forward 3 axioms for probability, and nowadays people use the axiomatic definition. So the axiomatic definition, if you say, it is pivoted on the 3 axioms. Kolmogorov proposed the 3 axioms as the a priori probability PA is greater than or equal to 0. Okay, that's the first axiom. Then the second is the probability of the sample space, that is P omega. Okay, P omega, that is equal to 1. Okay, then probability of a union like P A union B or A plus B, P of A plus B is PA plus PB, provided that A and B are mutually exclusive events. Mutually exclusive means one does not preclude the other. Like if a head is there, it cannot be a tail. If a tail is there, it cannot be a head. Okay, so things are mutually exclusive. So in this, these three axioms you have to understand very thoroughly. Probability of an event A that should be greater than or equal to 0. Then the probability of the whole sample space omega that is equal to 1, and P of A plus B that is equal to PA plus PB, provided that A and B are mutually exclusive events. And omega is actually the sample space and A and B are events. Okay, event is nothing but a proper subset of the sample space. This you have to understand very clearly. So suppose I have a coin toss experiment. If I make a single coin toss with omega, I have two elements in omega. The sample space contains H and T, the head and the tail. That is the sample space. And what is an event? Event is a subset of a sample space. How many subsets does omega has? It has got 2 raised to 2. That is 4 subsets should be there. So what is that? That should be either the head, okay, or tail next to one, or head or tail. HT is another subset of this thing, because any set is a subset of itself. And then the null set. Null set is a subset of any set. So there are 4 subsets. These subsets are called events. Event should be that thing should be completely should be correctly understood. What is sample space you have to understand, and what is an event? Event is actually a subset of a sample space. In fact, it is a proper subset of the sample space. So here I can assign probability to these events. Say like if it is H, there is a probability of getting a head, okay, which is 0.5. So I can assign a probability to this event, that is getting a head. Then getting a tail, that is probability of a tail, that's a half. Then probability of getting a head or a tail, which is 1. Actually, this is the whole sample space. Probability of the sample space should be 1. Probability of getting a head or a tail, because it should come as either head or tail. So the probability is a 1. Then what is the probability of a null event? That is an impossible event or null event. So that probability is a 0. So I can assign probability to all these subsets or events, but there are certain infinite subsets, etc., on which I cannot assign probability. They are like the set of infinite primes, etc. I cannot assign probability to such cases. So all subsets excluding such bad subsets. So whatever subsets on which you can assign probability, that is called a Borel field. Okay, it's called a Borel field. A field is, simply speaking, it is a set. Borel field is a set of all subsets, excluding all bad sets. You can assign probability to every element in the Borel field. Okay, so probability is a function. I can treat it as a function with a domain as a Borel field, and range as the real numbers from 0 to 1. You know that any function y equal to fx, if you say x is the domain and y or fx is the range of the function or codomain of the function. So it's a mapping from the domain to the codomain. So probability can be treated as a function or a mapping from the domain, that is a Borel field, or all or proper subsets of the sample space, simply speaking, to all real numbers from 0 to 1. And so you understood the concept of a sample space, then the subset of the sample space, that is called an event, and then that trio omega fp. Omega is the sample space, f is the good subsets of the sample space, and probability is a function over that, or the probability assignment over that. This trio omega fp, this trio is called experiment or probability space. So you should not confuse the word experiment with scientific experiments. Experiment and probability is completely different from scientific experiments. Don't confuse that. The trio omega fp is called the experiment. It's also called the probability space. Omega fp, that is called the probability space or experiment. And when I come to the end of this video, the summary, if you say what you learned in this video, or you reviewed the theory of probability, then you observed a coin toss experiment with Python and you verified the law of large numbers. You can write similar codes and execute on your machines. Then you revisited the 3 definitions of probability. Then you learned the meaning of sample space, event, Borel field, and experiment. And that is the end of this presentation. I thank you all.